All right, so today we are going to be starting with something that looks very complex, and we're going to be graphing it. Now, when we see these types of complex equations, what we're going to be doing is we're going to start by simplifying it. And so step one of this problem is to simplify. Now, remember our process. It's been about a week since we've done a whole lot of simplifying. The very first thing we do then is we factor our denominator. Yes, that is factorable. In this case, it's going to factor down to x plus 5 times x minus 3. Notice what that does for us. The x minus 3's are going to cancel out, which means that this original equation is equivalent to just y equals 1 over x plus 5. Whereas looking at this equation up here, it wasn't really graphable based on the form that we saw. This is very graphable. This is in a form that we are used to seeing, that we're comfortable with. In fact, it shouldn't be too hard to graph it from that. It's just that when we do so, we still have to consider the other part of our simplification process. Because remember last week, we had simplified one of these, and whenever we simplified, what did we have to remember to include? Yep, it's what x cannot equal. That is the restrictions. And the restrictions are anything that ever would make the denominator equal 0. And you notice there's two of them in this case then. X cannot equal negative 5 and positive 3. Now, when we start graphing this, we actually start just straight up from our simplified equations. We're going to end by dealing with the restrictions and seeing how that impacts the overall picture. So to start with, we draw our asymptotes as usual. And as I take a look at this equation, y equals 1 over x plus 5, it tells me it's being shifted left 5. So you can see there our asymptote is left 5, and the other one hasn't moved up or down at all, so that's why it's at 0. And then we need to plot our first point. Where does our first point always go? It goes at 1, 1. And so my very first point goes right 1, up 1. And notice there's no reflection, there's no stretch that changes that. So that's why it's still just over 1, up 1. All right, from there, remember we need to give 2 points on this side and 2 points on this side so that we can get a pretty nice idea about how that curve is going to look. Remember to get those points. What we're doing is we are just doing the reciprocal of whatever it is. So like if I go over 2, the reciprocal of 2 is 1/2. Alternately, if I go over a half, the reciprocal of 1/2 is 2. So I go over 1/2 and up 2. You can do that to get any points that you want to over here. Remember the general rule of thumb is give me 5 points in each quadrant if they'll fit. All right, so we got the points in the upper right. Now we need the points in the bottom left. Same idea, except we just switched directions. So like for our first point, we went right and up. Well, for this one, for our first one in the bottom left, we're going to go left and down, but by the same distances. So we go left 1, down 1, and we can do the same thing to get all the other points as well. So for instance, like this right 2, up 1/2, that's going to become left 2, down 1/2. Once you plotted the points that are in the upper right quadrant, you can just use the same patterns you use there to transfer them over into the other quadrant. And so then we got enough points in to go ahead and draw the curve, so we draw the curve in through it. And this is our graph of just the y equals 1 over x plus 5. But it's not quite correct for the graph of the original. It's almost perfect, but we got to tweak one little thing. Because remember we had restrictions when we simplified it. You can see already that one of the restrictions has already shown up here. The negative 5, that's our asymptote. So restrictions are asymptotes, but not only asymptotes. This 3 here, it also plays a role. Something is happening over here where x is 3, because this does equal this except when x equals 3, which means that this thing is broken at 3. Because remember, if I tried plugging 3 into the original one up here, I'd end up with undefined. It's impossible. I'd be trying to divide by 0. There can be no value at x equals 3. So how do we show that? We actually draw an open circle, an open dot at that point. So what you do is you erase that one tiny little piece of graph so that it's actually still going to be open inside of your circle. And then you draw an open dot there where x equals 3. Now, basically it looks like we just put a hole in the graph. Well, we always love to have fancy name for things in math, right? So, what do we call that hole in our graph? A hole. Okay. You can get fancier if you want to. You could also call it a removable discontinuity. I'm going to stick with hole for now. So, holes will appear in the graph any time that we end up with a restriction that's not an asymptote. And we represent them as an open dot. It might be useful to make note of those details here by writing down this information about what a hole actually is and how it shows up. All right, so now that we've seen the holes, we want to see how this simplifying kind of process affects the domain and range. And so since domain is the possible x values, here our domain is going to be all real numbers except where x equals the asymptote. So x cannot equal -5, but also now we see that x cannot equal wherever the hole is. So x cannot also equal 3. All right. Now having seen that, one little detail to note here, that's the same as our restrictions, right? And that's always the case. The domain and the restrictions are really the same thing because restrictions are just restrictions on the domain. But then for the range, our possible y values, of course, we still are going to start with where the asymptote is, so y cannot equal 0. But also, just like we had with our domain, the hole is going to affect the range as well because there is this one y value here just above the asymptote that passes through that hole, where that line, if drawn perfectly through that hole, will not touch the graph anywhere. And so it has to be excluded from the range as well. Now how do we know where that is? You can actually take that hole value and plug it into your simplified equation. So if I plug the 3 in there, 1 over 3 plus 5 is 1 over 8. It equals 1/8. All right, so for our second problem here, we're asked to graph this. Again, the original problem is not in an easily graphable form. And whenever we see a math problem that isn't in something that's easily worked with, we look to see if we can manipulate it and make it into something that is. And so my first step is to simplify. So, first step in simplifying is to factor. Once we've factored it, now I can take care of the division part, which means flip and multiply. Multiply all of that into a single fraction, and then cancel where you can. That looks a lot more promising. But of course, this is not totally the final answer. This is not the totally simplified form, right? What else do we need to add in here? Restrictions, yeah. Because we always still have to say, what can x not equal? In other words, what would ever have made the denominator equal 0 throughout this problem? And so in our final answer, we can see that x cannot equal 1. But if we look up above there, we also get 2 and -1. And so we have 3 restrictions in this particular example. This is now what I'm working with in order to graph it. So for the graphing process, step 1 was to make this. Now that I've made that, I don't need to look at anything else in order to make the graph. So let's actually start by just making sure that we understand kind of which part we're graphing here. The parent function here. This graph is going to be the same as what parent function, just kind of moved around a little bit. That's just 1 over x. So when we talk parent function, we're saying that I'm just going to graph 1 over x like I normally would. Just I'm going to be shifting it a little bit. That's what this does. Specifically, it shifts it right 1. And basically, normally this is a part that you're doing almost instantly in your head in order to be able to figure out where the asymptotes are. Because as soon as you see where those asymptotes are, you draw those on your graphing grid. All right, so then to start plotting our points. There's no stretches or reflections or anything, so my first point is still going to be right 1, up 1. And then for my other points, I'm just doing the reciprocal of whatever x value I choose. So for instance, when x is 2, I go up 1/2. Or if x is 5, because I'm going over 5 for my asymptote, I'm going up 1/5 from the asymptote, etc. I repeat the process on the bottom left. And so I go left 1, down 1, repeat the process for the other ones there, and then I can draw the curve through, but hopefully in pencil, because remember, we're going to have a tiny amount of erasing to do, because there's going to have to be a couple holes in this thing. Remember, the holes come from our restrictions. Now, the first restriction that I have listed there at 1, that's my asymptote. So that's already been taken care of. So this one is done. But you notice at 2, where x is 2, that one, there isn't anything yet shown. I have to show that the 2 is not really part of it. So what you do then is you erase that dot that you plotted, and you replace it with an open circle there. We then go to our next restriction, which was where x is -1, and I go down to -1, and I repeat that same process. I'm going to replace that dot with an open circle. And so then this is what your final graph should come out looking like in the very end. Now, a couple of you might actually put the open dots in as you first were plotting your points. That's fine. You can go ahead and do that. I often find it easier to just focus on one thing at a time, so I just tend to save that for last. But you can do it whichever way actually is consistently, intuitively correct for you. And hopefully you're starting this one by trying to simplify. In this case, addition. We already have a common denominator to make life easy. So you're hopefully starting by just adding the like terms on the top. So after we combine like terms, we factor on the top so that we can look to see how we can simplify it. And you'll notice that that gives us an x minus 5 that's going to cancel out on both top and bottom, leaving us with x minus 4. But notice that that x minus 4 that we're left with is on the top. What's left on the bottom? 1. And so this really then equals x minus 4 over 1. Okay, well, we don't really need to write x minus 4 over 1, do we? X minus 4 over 1 is x minus 4. And so all of a sudden we see that we can be graphing one of these rational expressions, and it's going to turn out not to be a reciprocal function. Now, this is simplified, but our answer for our simplification isn't totally correct yet, right? Did you remember to include the restrictions? In this case, the only thing that ever appears in the denominator is this x minus 5. So we only need to say that x cannot equal 5. This is now the graph that I'm going to be making. Well, let's think about what this would actually look like. What is the parent function for y equals x minus 4? Well, notice it's not 1 over x because x is not in the denominator here. Well, really, it's just y equals x. Yeah, it's just y equals x. What's the shape of the graph of y equals x? Yep, it's just a line. Transformations. Well, we are changing the graph of y equals x a little bit because we have this minus 4 hanging on the end. It is hanging on the end, so that's moving it up and down. So we'd say that this one is shifted down 4. And then normally I'm asking you, what are the asymptotes? But in a line, there is no asymptote. So notice, it's not going to be the same looking graph as what we've been doing. It literally is just going to be a line. And so to make my line, the very first thing I do is I put my first point down 4. Having plotted my first point, I can now go ahead and start drawing in my line. Well, normally we go to the idea of slope for that. What's the slope in this equation? 1. because like there's a 1 in front of that x, which means that from my first point, I'm going to be going up 1, over 1. And then from there, up 1 and over 1, and up 1 and over 1, and up 1 and over 1, over and over and over again, until I can go ahead and draw in a nice, neat line through there. Now this is a great looking graph for y equals x minus 4, but it is not yet the graph of y equals x minus 4 where x cannot equal 5. How do I count for the x cannot equal 5? We got to put a hole in it. And so we go over to where x equals 5, figure out where the graph is at that point, and replace that point with an open dot. And when you've done that, it now does reflect this exactly, and therefore reflects that whole thing exactly as well. So this is then our final graph. So you can see the simplifying process sometimes is going to give you different shapes of graphs. You have to let the resulting equation tell you about what it's going to look like.